Our galaxy is pocked with star-forming regions. They are dominated by powerful stellar winds, harsh radiation, and swirling dust clouds. Here, gravity, the great cosmic sculptor, crafts new stars, and within their fold, solar systems. From these chaotic regions, clusters of stellar siblings move out from their galactic nurseries. These young star clusters form moving groups, bound together by gravity, that wander the plane of our galaxy. Since the late 1990s, astronomers have been probing these moving groups for evidence of planets. They may yield clues to the origins and early days of our own solar system. Using the precision technologies of the European Southern Observatory in the mountains of Chile, astronomers finally found what they were looking for. They peered into one of the most famous of all moving groups. M67, also known as the King Cobra star cluster. King Cobra lies about 2,500 light-years away in the constellation of Cancer the Crab. It contains about 500 stars. They are all about the same age and composition as the Sun. The astronomers monitored 88 selected stars in the cluster over a period of 6 years, in an effort to detect subtle wobbling motions caused by the gravitational tugging of planets. They found 3. Each of these planets is what's known as a hot Jupiter, giant gas planets that orbit perilously close to their parent stars. One of these stars is almost identical to our Sun. In fact, our Sun was once thought to originate in King Cobra. It would have been hurled out during a gravitational encounter with one or more other suns. Recent analysis shows that to reach its present position, the Sun's exit would have been so violent that its planets or planet-forming disk would have been stripped away. Now, 5 billion years after its birth, all obvious traces of our Sun's birth have been obscured by the slow evolution of our galaxy. But there is another moving group nearby that astronomers are watching closely for clues to the Sun's early days. The Beta Pictoris group has the distinction of harboring the first extrasolar planet detected without a parent star. Called PSO J318.5-22. It's 6 times the mass of Jupiter and a mere 12 million years old. Was this newborn planet, shown here in an artist's drawing, hurled out of its solar system by another larger planet? Or did it somehow form by itself? And how many others like it are roaming the back roads of the galaxy? The 28 stars of the Beta Pictoris group are centered about 115 light-years from Earth. They are all young, at 10 to 30 million years old. Most are so dim, they are not visible to the naked eye. There is one star that is. Beta Pictoris is nearly double the mass of the Sun and almost 9 times as luminous. It emits a torrent of infrared light, a sign that it is enshrouded by large quantities of dust and gas. Beta Pictoris has the first circumstellar disk ever imaged around another star. The disk is filled with comets, dust, and hordes of tiny objects called planetesimals. This debris disk is presumed to be the source of a stream of particles heading toward us from the direction of Beta Pictoris. Astronomers suspect that it may be a dominant source of interstellar meteoroids in our own solar system. These tiny objects were likely thrown out beyond the disk by the movements of larger planet-sized objects. In fact, by blocking the bright light of the star. Astronomers were able to spot one large planet within the innermost region of the disk. 5 years later, the planet was gone. Then it reappeared as it moved to the other side. This planet, between 4 and 11 times the mass of Jupiter, orbits at about the distance of Saturn to the Sun. Beta Pictoris b is having a powerful effect on the circumstellar disk. With its immense gravity, it is sweeping up large volumes of gas and dust. NASA scientists sought to simulate the planet's role in the evolution of the disk and to explain its odd contours.
When we view Beta Pictoris at longer wavelengths, people claim that there's a warp in the center of the disk. At shorter wavelengths, it looks more like an X. And we haven't really understood until now how those patterns were related.
Our simulation is the first model that can capture the 3D structure of the disk, as well as the collisions that are occurring between the planetesimals in the disk. So if we look at our simulation results edge-on, the same way that we see the real Beta Pictoris disk, then we see this warp structure that's created because the planet is orbiting tilted with respect to the disk. If we look at our simulation results face-on, which is a way we can't see the real disk, then these face-on simulation shows this spiral density structure of the planetesimals. And this spiral is created because the planet's on an eccentric orbit. It's not a perfect circle, it's an ellipse. When the spiral created by the eccentricity of the planet intersects with that vertical wave from the inclination of the planet, the collisions are enhanced in some places and damped out in others, which creates this clumpy collision structure.
If you look at our model in cross-section, you can see the crests and troughs of the wave, where the collisions are enhanced. Like an ocean wave, in front of the wave it's calm, but then the crest comes along and lifts the planetesimals out of the plane. And then there's a trough, and then the wave starts wrapping around tighter and tighter. And then it's almost like foam on the backside of the wave. The planetesimals get all stirred up and start colliding with one another and breaking into dust. We've learned so much about Beta Pictoris over the years, but all the little pieces of evidence didn't seem to fit together before. This model tied together in a nice, neat package the story of Beta Pictoris and its planet.
The action of the planet hints at a larger dynamism of the debris disk. As far back as the 1980s, astronomers studying the starlight of Beta Pictoris saw motions they couldn't readily explain. Because these motions came and went over hours and days, the astronomers speculated that they were caused by starlight shining through plumes of gas thrown off by icy bodies that were diving through a debris disk. Recently, the same team used planet-finding technologies at the European Southern Observatory to study these comets. They found that the orbits of these comets are remarkably close to the star, an intriguing snapshot of the chaotic early days of our own solar system. The story of these comets doesn't end there. Working with the ALMA telescope array in Chile, another group looked at chemical variations in the disk. They detected a belt of carbon monoxide gas about 3 times the distance of Neptune to the Sun. It amounts to 200 million billion tons, equivalent to about 1/6 the mass of Earth's oceans. The cloud is a puzzle because incoming ultraviolet light should be clearing it out by breaking up the carbon monoxide molecules at a much faster rate. That means the gas is being continually resupplied, most likely by the breakup of icy comets. This is happening at a rate equivalent to the total destruction of a large comet every 5 minutes. So what's causing all this havoc? The source is likely waves of collisions linked to huge comet swarms. The comets would have been shepherded together by an as yet undetected second planet, whose gravity confines them into a small region. This second planet should weigh in at no less than the mass of our Saturn. Based on the contours of the larger debris disk, astronomers suspect there's a third large planet, 10 times the size of Jupiter, further out, as well as a host of planetary embryos as large as Pluto on the fringes of the disk. In time, Beta Pictoris, like our Sun, may well detach from its siblings and the moving group in which it was born. Much of the loose gas and dust with its disk, like that of our Sun, will gradually be swept up by planets of different sizes and orbits. Will any of them be Earth-like? Because the star is much hotter than our Sun, the orbit of this Earth-like planet would have to be around 3 times larger than that of Earth, at about the location of our main asteroid belt, with an orbital period almost 4 Earth years. Present methods are not able to detect a planet this small. If and when our technology allows us to push in this close, it may yield remarkable clues to the early days of our own planet. How quickly did it cool? When did an atmosphere develop? What was its chemical composition? How early could life have developed? In a sense, when we peer into this restless new solar system, we enter a time warp, one that takes us back to our own deepest roots.